Welcome everybody. This is a short introductory video to the polar form of complex numbers. So we start by introducing polar coordinates. So far we have used Cartesian coordinates for complex numbers, a being the real part and b the imaginary part, and the complex number is represented as always by this arrow. Now there's another possibility, Now there's another possibility of describing how to get from the origin to the end of this little arrow here, which is by telling you how far you must go and the angle towards the real axis under which you must travel. And this pair here, r for radius or length, and phi, the angle with the real axis, this pair is called polar coordinates of any complex number except for 0, because obviously for 0 the angle would be not unique. So, and talking about uniqueness, we want the angle to be in the interval from 0 to 2 pi, because otherwise I could use this angle plus 2 pi or plus 4 pi or whatever, and uniqueness would be lost. And r is nothing but the absolute value of z, or the length of this arrow, and the angle phi is sometimes called the argument of the complex number. And then using trigonometry, of course, we have that a, the real part, is nothing but r times the cosine of this argument angle here, and the imaginary part b is nothing but r times the sine of this angle. And plugging this into the Cartesian form gives us the polar form, or better, the useless polar form. We're gonna see in a minute what I mean by that. And I can pull the r out, so this here would be the polar form of a complex number. Cosine of the angle plus I times the sine of the angle, and the whole thing times r, the length of the arrow. Usually I write bi, but sine phi I looks strange, and also I would have to put brackets here, which I want to avoid. That's why I pull the I here in front of the sine when I write the polar form. Okay, let's look at some simple examples. First of all, when I have polar coordinates, for example 2 and pi over 3, then it's very easy to write down here the polar form of this complex number. Simply plug in 2 here, and for phi, pi over 3, and then using a calculator or knowing it by heart, cosine of pi over 3 is 1/2, and the sine of pi over 3 is the square root of 3 divided by 2. Multiplying out by 2, I end up with 1 plus square root of 3i. So why did I write useless polar form? Because obviously this is a much neater way to describe the complex number than writing down this whole expression. We're going to see in a little while why it is useful nonetheless to introduce polar coordinates, but so far it doesn't really make sense, or doesn't seem like any improvement. Okay, next we have a complex number in Cartesian form. We want to transform it into polar form, or find the corresponding polar coordinates for this number here. Then of course we start by calculating the length using Pythagorean's theorem, which is 2. And just by looking at it, we see that the angle is 45 degrees, or pi over 4. And if this is not obvious, then you simply use that the tangent of this angle here is b divided by a here, and you use your calculator to calculate the arctangent of this expression, but this in this case here is 1, and the arctangent of 1 is pi over 4. So we could also write the number like that. And again, you don't see what advantage this should bring, but be patient. Another example, where the arrow lies in the fourth quadrant. The number is 3 minus square root of 3 times I. The radius, or r, of the polar form is again no problem. Simply using this formula, you end up with 2 times square root of 3. And when you calculate the argument using this formula, you obtain arctangent of minus square root 3 divided by 3, and your calculator gives you minus pi over 6. But now we wanted our argument to be in this interval. So the tangent has a period of pi, so you start adding as many pi's as possible until you end up here. In this case, you have to add 2 pi, and then you end up with 11 pi over 6, and this is indeed in this interval as required. And then we end up with this expression. And again, you might ask yourself, what the hell am I doing here? What's the use of the polar form? So far there isn't really any, but in the next video we are going to prove Euler's very famous identity, namely that an expression like this can be expressed as E, Euler's number, to the power of phi times I. And this here, this is the real polar form, opposed to here the useless polar form. This brings a lot of advantages when dealing with complex numbers, and this is one of the most important formulas in complex number theory, or in a lot of areas of math. It's very, very useful to have this identity. So, thanks for watching. Please stay tuned. See you then.